Hi, I'm Sam and I'm presenting this joint work with Timon, Petar, Laurent and Martin from ETH Zurich. Traditionally, network verification is concerned with checking properties such as reachability and often also takes failures into account. And there is a long line of existing work that can be used to reason about such properties. And you can, for instance, check the property for a specific failure scenario, or check whether the property holds for all scenarios in some set. And because in those cases the property either does or does not hold for the considered set of scenarios, we call these properties hard properties. In reality, the failures within a network are probabilistic, so nodes and links fail randomly. So we can lift the question about property satisfaction to this probabilistic setting and ask, what is the probability that the property holds? And this is a very practical question. So consider a service level agreement specifying that reachability is guaranteed 99.99% of time, or with probability 99.99. And there are also other properties whose probabilistic analysis is interesting. For instance, consider a network operator that wants to have load balancing, but maybe not 100% of the time because this would be too expensive, but 80% of the time would be okay. And as these properties are allowed to be violated for some fraction of time, we call these properties soft properties. When analyzing these, high precision is usually required. For instance, to verify these 4 nines SLA, you will have to obtain an imprecision below 0.01%. So what can we do to compute the probability of the property? It eventually boils down to exploring the failure space. And one simple attempt would be to explore the scenarios in the order of likelihood. So you would start with the scenario where you have no failures, and then check the property, and then explore all scenarios with exactly one link failure, and so on and so forth. In a network with 191 links and some realistic failure probabilities, the number of scenarios to be visited in order to achieve a 4 nines precision is more than 1 million. And this is clearly too expensive, right? Running an existing verifier for each of those scenarios. Alternatively, you can perform probability estimation using samples. So you would just repeatedly sample from the failure model and check whether the property holds. So using concentration bounds such as Höfting inequality, you can show that you need at least 700 million samples here in order to achieve a 4 nines precision. And this is clearly also too expensive. So in this talk, I'm introducing NetDice, which reduces the number of scenarios to explore to a bit more than 1800, which is around a 600 times reduction compared to partial exploration. NetDice is a probabilistic network configuration analyzer supporting BGP and IGPs, high accuracy sufficient to verify 4 nines SLAs, and which is scalable also for large networks. How does NetDice work? As input, it takes a network configuration of routers supporting BGP, OSPF, ECMP, and static routes. Next, it takes a powerful failure model that can model dependent link nodes and SRLG failures. It also takes a property and then computes the probability that this property holds in the network under the given failure model. Let's have a look at the properties supported by NetDice. And assume that in this network, traffic arriving at ingress A towards destination shown here is forwarded as shown in the graph. And NetDice is interested in checking properties solely based on this forwarding graph. And you can check many things. You can, for instance, check reachability based on the graph. You can also check a path length for a waypointing requirement. And all those properties are called single flow properties because they only depend on the forwarding graph of the single flow. Of course, you can extend this and reason about multiple flows such as isolation in what we call multi-flow properties. NetDice targets few flow properties, where the set of flows under consideration is small. You can analyze any such property using NetDice as long as there is an efficient check of the property based on the forwarding graphs. How does NetDice prune the space of failures? Consider this network here, which uses shortest path routing, where all links have weight 1 except the link in the center. Traffic from A to B is forwarded along this path. Of course, if this link here fails, then the shortest path will change and traffic will be forwarded as shown here. However, under this failure here, the shortest path will not change. It is a very important observation that any failure outside the shortest path will not change the shortest path. So we capture this idea in the notion of cold edges. The cold edges are those edges whose failure are guaranteed not to change the forwarding graph. In these examples, all edges outside the shortest path. There are actually 32 equivalent failure scenarios with the same forwarding graph. Any combination of failures of the cold edges will lead to the same forwarding graph. The key technical contribution of NetDice is how to identify cold edges for common routing protocols. So let's introduce a static route as shown here. Now, traffic will be deflected by the static route as shown in the figure. What are the cold edges here? Of course, if any of the green links fails, then the forwarding graph will change. But there are also other failures that would change the forwarding graph. For instance, if this link fails, then the shortest path from A to B will change and A will not forward traffic to the right in the first place, but will use the following forwarding path. So how do we find the cold edges here? So NetDice actually reasons about the opposite, which is edges whose failure may change the forwarding graph. We call those edges hot edges. We have already seen that the edges along the shortest path from A to B have to be hot, because any of those links failing will change the forwarding graph. Additionally, also these edges here have to be hot. By taking the complement, NetDice arrives at the set of cold edges. In our paper, we show an algorithm to identify the cold edges for BGP. This algorithm takes into account network partition, the semantics of route reflection, and the dependency between BGP and IGP. You can have a look at the paper where we also provide a correctness proof. So let's see how NetDice explores the space of failures. It starts with S0, the scenario without any failures, and then constructs the forwarding graph and checks the property. Now it identifies the set of cold edges, and the idea is to implicitly cover any failures of those at once without exploring these scenarios. To this end, it computes a probability mass of all equivalent scenarios, which are the scenarios that have cold edge failures. And this probability mass is much higher than the probability of the no failure state alone. Now it simply recursively introduces failures of the non-cold edges, so it would let this edge fail, construct a forwarding graph, let the remaining edge fail, construct a forwarding graph, and then apply this technique recursively. And while doing this, it has to take care of not exploring states twice. So NetDice explores a tree of failure scenarios and simply sums up the probabilities of those where the property holds. It cuts off unlikely scenarios to speed up inference. The efficiency of our exploration depends on the number of cold edges. NetDice is very efficient in practice. We implemented NetDice, and you can find its implementation supporting some common properties on GitHub. For single flow properties such as reachability, NetDice only uses few minutes in networks of hundreds of links to reach a 4/9 precision. For 80% of the scenarios, more than half of the links are cold. For multiflow properties, NetDice's performance degrades gracefully. As we show in the paper, we also analyzed a real ISP configuration. In summary, NetDice is a precise and efficient probabilistic network configuration analyzer.
Great, thank you for the nice talk. So Samuel is online now, and please feel free to ask him questions. Well, we have many questions coming in. So the first question is from Aaron. Is how does determination of hot and cold edges interact with equivalent classes?
So the thing is, by identifying cold edges, you somehow get the equivalence classes immediately, right? It's very similar in spirit to the previous talk we've heard, meaning that once you know that some edge is cold, then all kinds of failure combinations involving this edge belong to the same equivalence class, right? So when you explore this tree of failures, basically at every node you identify a whole equivalence class by looking at the set of cold edges. So it's basically the same idea.
Thank you. The next question is from Ali, which is, in addition to supporting link failure kind of probabilistic events, are there other probabilistic events you can potentially support?
Yeah, so in terms of failures, we support a very expressive model. So you can also model node failures or shared risk link group failures. That's not an issue. We have a strong model there. But in terms of other probabilistic events, for instance, probabilistic BGP announcements could be, for example, NetDice can currently not handle that and is focused on network component failures.
Great. One last question. Is there any good opportunity to scale NetDice for multi-flow properties?
I'm not sure whether I understand the question. So in terms of multi-flow properties, NetDice starts to degrade, right? For instance, if you check all the flows in your network, like n squared, if you have n nodes, then NetDice will not work at all because there won't be any cold edges there. What we are focusing on is for instance, something like isolation. So let's say you have two heavy flows or two flows that must be isolated for reasons of security. Then you can use NetDice to analyze those kind of properties.
Great, thank you very much. Congratulations again for your student work. And there are a lot more other questions coming in Slack. Please try to answer those there.
Thank you for a really nice talk. And I neglected to mention at the beginning, this is also one of the award papers. So congratulations on the Best Student Paper Award, and also a paper that received all of the artifact evaluation badges, which again is great to see folks releasing open source artifacts that can be used by others. So folks who have questions, please either type into the Q&A in Zoom or on the Slack. I see some pencils writing on the Slack. I'll quickly ask, I'm curious if you've had any experience talking to network operators and what are their thoughts on this kind of probabilistic analysis?
Yeah, I mean, we did some sort of analysis by doing some survey on the NANOG mailing list. So we asked operators whether they would actually use such a tool such as NetDice. And it turned out that actually a lot of them would be interested in such an analysis because they currently model or kind of they have models of these failures. They know how often those links fails and what are the issues and what's not. And but the only thing they're currently doing is just analyzing it in practice or do some kind of simulation, but they don't have a tool that computes these kind of probabilities such as NetDice does.
Great. A question from the Slack from Ratul. He says, isolation smells like a hard property because it's security related. Is that the right intuition?
Well, the intuition is correct, but it's not about the security here. The thing is, when you start to include more flows, then you will have more hot edges, right? So if you only look at two flows, then you basically the same reasoning applies as you have seen in the talk, but you need to union the hot edges as these flows may interact. But if you start to look at all the flows in the networks, then NetDice starts to become slower and slower simply because it's very hard to find any edges whose failure is guaranteed not to change any flow under consideration. But like the security aspect per se is not harder than any other aspect of a property.
Another question about the performance. Is there a performance impact due to realistic BGP policies? I think the question here is, were the examples you considered somehow representative, or were they simplified in some way?
Yes, so for the policies, actually, it's not a scaling issue at all. So if you do a policy at the network edge for using eBGP routing maps, it's not an issue for NetDice at all. It's merely a pre-processing step that we are doing. So there's not an issue with those. However, we currently do not support policies inside the network. So if you start doing some crazy routing changes using IPGP policies, it's currently not supported because it's very hard to have some formal guarantees actually of what is going on in this case, and we will look into this for the future.
Great. So I have one more question. So this idea of pruning based on cold edges seems really nice and a very important optimization for making this tool scale. And it also fits well with the kinds of protocols you're looking at, which are mostly triggered by changes on edges. Have you considered more generally in sort of probabilistic analysis tools whether this kind of optimization makes sense? So finding some dimension of the problem where when the weight of something dependent on that aspect falls below a threshold, then you decide to not explore it. Do you think this technique is generally applicable? And I'm also wondering about like data plane analysis or other kinds of protocols besides the one you modeled, if it would always be edges, or might it be something else that causes you to prune?
Yeah, that's a good question actually. So the idea still applies. It's about identifying which aspects will actually impact what is going on. So in this work here, we really focused on the failures, particularly on the link failures during exploration. But I can imagine that you can apply similar reasonings with other things that can be pruned, and like the exploration would work exactly the same, right? So if you have some elements which are subject to some probabilistic effects, if you can identify any changes that will not change the property, then you can safely prune them. But of course, you have to sit down and kind of identify first what kind of elements that you want to prune, and second, you need to find an efficient way to identify those elements that you actually can prune.